Last week, I gave a lecture on the basics of climate change, and I also talked about how we need to go through everything from the basics to talking about volcanoes, the modern science, politics, and then some questions at the end. And the reason why I formulated the lectures in the way that I have, and the reason why we are focusing on volcanic eruptions today, is each one of these things is a humongous topic. So I figured if we broke it down into more manageable parts, then we'd be able to have the time for reflection to be able to think about it. I'd have time to create more videos. So when we talk about volcanic eruptions, one of the common refrains that I hear in conversations about climate change is this: volcanoes do so much more than people. So why are we worried about what we do when anything that we do is just superseded by volcanoes? And I understand what the idea is there. If I'm trying to keep my yard clean and I want to be able to sell my property and I want people to come through the neighborhood and look, that property's nice, it doesn't help me to sell my property if everybody around me is being dirty. So if I do this, if I go, okay, and on this day, the people are going to come by and they're going to see my property and my neighbor dumps a whole bunch of junk in their front yard, then what do we see? My property is just superseded by that, no matter how much good that I've done. And I think people look at the idea of volcanoes in that way. It doesn't matter how much good we do, blam, something that I cannot control, out it comes, and it supersedes it. So in order to understand that, we need to understand what volcanoes can do, what historical volcanoes have done, what really big eruptions could be, and then think about it in context. Volcanoes are odd because depending on the nature of the material that is erupted and the local variability in that material, you can get a range of different factors. What does that mean? When a volcano erupts, we could look at effusive eruptions like what we would see in Hawaii, where generally they are benign. We sometimes have to evacuate because the physical liquid is moving toward properties and they can't move, so we want to evacuate the people. But by and large, that material sort of oozes out of the ground, or even if it is energetic and it's shooting up into the sky, it's more like opening the top of a soda bottle. If it's been shaken, you get a splatter, but generally very little harm done. Versus the incredibly explosive volcanic eruptions, we see our classic picture of the cone with the massive cloud that erupts out of it and can affect the skyline, can create mud rain. We get the lightning blasts of those strange colors of lightning and all that stuff. So we can have those two distinct ends. Regardless of those, and I did a video on those, if you're interested, look at the video on volcanoes and volcano myths. Regardless of which type we're dealing with, the principal gas that is associated with eruptions, water vapor, carbon dioxide. We generally don't care about the water vapor, aside from talking about early Earth history, where we think volcanic eruptions may have helped add significant amounts of water to the atmosphere and then were instrumental in creating the world's oceans. But we talk about, oh, wait, you said carbon dioxide. Absolutely. If carbon dioxide is produced in sufficient quantities, carbon dioxide, we know, regardless of the influence of people, regardless of us changing the magnitudes of it, carbon dioxide is essential for helping keep the planet warm. And the first video we talked about that, how carbon dioxide's in the atmosphere, heat tries to be given off, and it plus the water vapor in the atmosphere is able to slow that heat loss so we stay warm enough until we get the next daily input of energy. So volcanoes produce water, which is a greenhouse gas. They produce carbon dioxide, which is a greenhouse gas. They can produce sulfur dioxide, which is a potent gas that can affect the temperature in the atmosphere. They can produce a whole host of other things. But those are the real big three, and the big two are water vapor and carbon dioxide. They can also produce what we call aerosols, which are essentially tiny little droplets of material that are kicked up and can be buoyed, especially in really explosive eruptions, high into the atmosphere. Well, who cares? We've all seen aerosol spray cans. You spray and out comes a mist of droplets. So volcanoes can produce a mist of weird droplets. Yes. But while carbon dioxide and water can help keep the planet warm by trapping some of the outgoing infrared heat energy from the planet, The aerosols actually have another effect. They have a scattering and reflecting effect, so that when they get into the upper atmosphere, sunlight shining down on them can reflect off of the Earth back out into space. If we increase the number of aerosols in the sky, less sunlight makes it to Earth, so the Earth is cooler. So volcanic eruptions can have a warming effect or a cooling effect depending on what is produced. So when we look at it, we have to understand that not every volcano is going to be, well, why is the planet warm now? It's volcanic eruptions. Not necessarily. Volcanic eruptions can produce a whole host of aerosols, which can actually cause climate cooling. So volcanoes are a good thing. We want more of those. Well, no, neither extreme is good, right? You don't want to be too cold. You don't want to be too hot. You want to be just right. You want to be the Goldilocks porridge, right? So don't they just counteract each other, like 1 plus, 1 minus, and they cancel each other out? No, not necessarily, because if a volcano produces more aerosols than it does the other gases, if it for some reason has a very aerosol-rich eruption, then you can have cooling outweigh any warming effects. You could have warming outweigh any cooling effects. Or you could have them produce these things, but depending on the nature of where they were injected into the atmosphere, some might have longer residence, so it stays in the atmosphere longer. And if it stays in the atmosphere longer, then we could have both things produced, an initial warming phase and then a long-term cooling phase. When we talk about long-term is a very dangerous word. And this is why I titled this Short-Lived Climate Change Events. Whenever you have an adjective, long, big, hot, we have to say in comparison to what? When most people think about something long-term, they think on the ages of decades or centuries or millennia. For the events that we are talking about, we are generally talking about on the years to maybe a decade. Even something like Yellowstone is hypothesized to have an effect that might last 8 to 10 years, with the magnitude of that effect decreasing with time. So an initial bad, and then it gets sort of better with time. So if we're talking on the order of 1 to 10 years, that's a short-lived climate change event. Because sure, it might be bad in the short term, but long term, everything goes back to normal. So we're going to look at 2 specific volcanic eruptions. One that was the first volcanic eruption to be linked to global climate, and then the more famous, the year without a summer. So, June 8th, 1783, some eruptions occurred in Iceland in what we call the Lackey-Fisher eruptions. So, Iceland on the left, we have Lackey here in the southern section of Iceland. In the upper right-hand corner, we have a zoom in, and we're sort of looking at where Lackey actually erupted from. And what you're seeing are lava flows that traveled great distances toward the Atlantic Ocean. In the lower right-hand corner, sort of a modern look at the Lackey-Fisher eruptions. That dark material that you see there is basalt, and everything else is weathering, lichens, and mosses that have grown on top. In 1783, we had a massive outpouring of lava in this region, and it did affect global climate. We had 130 craters that opened from water interacting with rising basalt magma. What is basalt? Basalt is an iron-rich magma. Well, technically, basalt is the substance that we have on the surface. So as it's coming up, eventually it erupts onto the surface and we call it lava. The stuff underground is magma. But we have this basalt that is coming up. As the material that would eventually erupt as basalt started interacting with water, it created explosive craters like the one that you see in the lower right-hand corner here. And lava started erupting out onto the surface. Eventually, that eruption started to decrease in violence, so we didn't get the soda effect where material is shooting up into the sky. It more oozed out across the surface, and cool, it's not as explosive, but you still had vast concentrations of lava. Well, who cares? Why would we care about flat soda if we're still talking about gas in the atmosphere? When we have gas, doesn't that mean that material is being ejected? In a way, yes, it does. So what's going on here? If I have that initial blast, I'm fluxing an incredible amount of gas into the sky as material is being shot upward, propelled by a large amount of gas. But what happens when that decreases in volume? As that decreases in violence. As it decreases in violence, when we have flat soda, we're not saying that it has no gas. We're saying that it has such low amounts of gas that we can't really taste it on our tongues anymore, right? We don't get the experience. So it tastes weird because we're used to the effervescence. It doesn't mean that there's no gas, it means that there's little. So why does that matter? Well, even if I have a small amount of gas that's there, it can still, as if that lava is erupted, still be administered into the atmosphere. So even when the violence started to decrease, the vast volume, it doesn't matter if it's flat or not. If there's a small amount of gas there, if I have a huge volume of lava, I still have a huge volume of gas. The total amount of material that was created, we call 14 cubic kilometers of material. So later on, I'll have a diagram of what a cubic kilometer of material is, but a kilometer is about 60% of a mile. So imagine a block that is 3,000 feet on a side, right? Because that's something easy to imagine. This produced 14 cubic kilometers of material over 8 months. So one scientist said, hey, what happens if we just, to try and explain to somebody, to really get them to go, wow, we just sort of pile all that material into a football field. Well, if you did, it would be a football field over 3,000 miles deep. So an incredible amount of material. Even if there was 0.5% of gas or 0.1% of that as gas, that is an incredible amount of gas. In most volcanic eruptions, the gas concentration is about 3 to 3.5%. So initially, we had 3% of that or 3.5% of that being ejected into the sky as gas. That's a tremendous amount of stuff. But even if we decrease that and we go, okay, well, the vast majority of that, though, 13 of those 14 cubic kilometers or whatever it is, was very flat soda. Even if we have 0.1% or 0.2% as gas, that's still an incredible amount of gas. The worst products, and this is interesting, this volcanic eruption tended to produce a lot of fluorine. Fluorine is not exactly a common gas that's found in volcanic eruptions. It can happen. This would be because of the local environment under the ground. There was a source that somehow fluorine enriched the lava as it came out. It produced 8 million tons of fluorine, 120 million tons of sulfur dioxide. If you're alive and you are older than 30 years, you've been alive through one of the largest eruptions of the 20th century, which was Mount Pinatubo. Mount Pinatubo, we have this classic mushroom cloud. If you watch my video on volcanic eruptions, we have a great discussion on Mount Pinatubo. Mount Pinatubo captivated people's attention because we could watch it on TV. We could see the unfolding mushroom cloud that's 20-some miles into the sky. And there was an incredible amount of gas produced in Mount Pinatubo's eruption. Here, the amount of gas that was produced would be the equivalent of one of those eruptions every 3 days. So we go, well, but visually, it wasn't explosive. No, it wasn't. It's more like soda that just happened to have a lot of gas, and we just have a lot of soda. So we could just keep on pumping the equivalent of that out. What's the difference? Well, the difference is this. Having one cigarette isn't necessarily good for you. Having many cigarettes, that's bad for you. And that's what we're talking about here. In Iceland, it killed about 20 to 25% of the total population due to a combination of famine, as the volcanic eruption killed the crops, and fluorine poisoning. And over half of all the livestock died from fluorosis, because as the aerosols, which contained the fluorine, would settle, then the cattle, for example, would go out, cattle and sheep would eat the vegetation, and they would ingest fluorine, and it is toxic to the body in large concentrations. So what about the global effects? Well, the picture on the left, this is a picture of the Laki fissure eruptions. And the reason why we call them fissure eruptions, if you look from the lower right-hand corner to as far as you can see into the distance until it gets whitish in the background with the glacier, we see a line through that image and then a whole bunch of pockmarks around it. And this is a typical thing that we would find in Iceland. Why? Because Iceland is a volcanic nation. It is built from basalt eruptions that have happened over many, many millions of years. On this image, what is happening is Iceland is being stretched. One side is pulling one direction, one side is pulling the other direction. And if I take a piece of paper and I pull on it, I'm going to get a tear. Because Iceland is being stretched, periodically there are places that are weaker than others, and they tend to tear in fissures. And then what you would see lava shoot out in what we would call a curtain of fire, like is shown in the lower right-hand image. And then over time, some of that tear, some areas will be more vigorous than others. So certain areas will cool down, other areas will keep going. And so even though they're still generally in a line, now instead of having one giant curtain of fire that shoots out, we're going to have a whole bunch of individual little craters, all relative to that line. So what would be the visual? This would be like the perforated page. We have all the holes. We know that we can tear it along there, but now it's just separated into a bunch of little holes. Right? This volcano also produced a massive amount of aerosols. So what happened? Originally, since they were delivered to the atmosphere fast in that initial period of violence, they trapped heat. That heat caused one hot summer. But because now the heat still needs to escape, and it's been retarded in its ability to escape. But over time, remember, we need new heating from each day to make up for the loss that we had each night. Well, the aerosols actually reflected some sunlight back, and over time, as the heat bled out, right, was eventually able to make its way out into space, we didn't get enough renewed heating to make up for the loss. So over time, atmospheric circulation was affected. It blocked sunlight, global cooling in 1784. And because of that, because of the aerosols in the sky, you could look up at the sun and the sun looked red. They called it the blood-colored sun. We had ice in the Mississippi River, ice in the Gulf of Mexico. The Mississippi River froze for a period of time. Now, it didn't freeze completely, but there was a lot of ice in the Mississippi River. And we had what we called the lackey haze, which was a fog that seemed to develop on the ground because we had cooling and the particulate matter in the sky. So who cares? Benjamin Franklin noted this because he was in Europe at the time, and he said this: there existed a constant fog over all Europe and a great part of North America. This fog was of a permanent nature. It was dry, and the rays of the sun seemed to have little effect toward dissipating it, as they easily do a moist fog arising from water. They were indeed rendered so faint in passing through it that when collected in the focus of a burning glass, they would scarce kindle brown paper. The vision I have is of Benjamin Franklin like out in the street with a burning glass, trying to actually burn paper, and it's not working. Of course, their summer effect in heating the earth was exceedingly diminished. Hence, the surface was early frozen. Hence, the first snows remained on it unmelted and received continual additions. Hence, the air was more chilled and the winds more severely cold. Hence, perhaps the winter of 1783 and 84 was more severe than any that had happened for many years. That's a lot of hences. He was the first person to make a specific link between global climate and volcanic eruptions because he happened to be there at the time. Now, Iceland has had many eruptions. It's a volcanic nation. We could talk about some of the crazier eruptions where they have the town of Vestmannaeyjar on Jaime, where they actually fought a volcanic eruption as the lava poured out into the street. They went, we're surrounded by water, let's bring in firefighters. And they basically just outlasted it. But this is the most dramatic and the most famous of the volcanic eruptions in Iceland's history because of its influence on global climate. But think about what that means. He didn't say 1783 to 1812, he said 1783 to 84. So even though this was a dramatic amount of material, both erupted in Iceland, killed a quarter of their population, half of their livestock, it affected the global climate for a year. So we have to put this into perspective. Massive eruption, 1 year. All right? Iceland has had other ones. In 2010, we had the eruptions of Eyjafjallajökull. And here's an example. I don't know if you remember this, but if you were watching the news at that time, there were so many reporters who were finding people in London, for example. They couldn't fly out of Heathrow. And because there was a volcanic eruption in Iceland and the atmospheric motion carried the material to Europe and dumped it on Europe, and it shut down a lot of air traffic. Okay? And it was funny because when they would interview people, they would go up and they'd find, for example, let's say I'm an American, for an example, they would stick the microphone in their face and they would say, so what do you think about all of the plane closures so that you can't actually fly back to the States? And they would give that look like, this is bullcrap because I can't fly back to the States. And I'm like, you're in London, right? This isn't some random out of the way, but you're in London. But one of the things I never saw on the news is what happened to the people in Iceland. They didn't seem, now one could argue, well, it's hard for the media to get there. Iceland has media, but we never heard what was really going on in the ground in London. It was always tourists that were disenfranchised because they're stuck there. And I'm like, you wanted to go to Europe and now you have extra time to be there. I understand that it's an inconvenience, but you're in Europe, right? So volcanic eruptions are not new to Iceland, but sure, this affected air travel, but it didn't affect global climate, right? The climate didn't even recognize that we had such an eruption, right? Now, let's look at the most egregious example in recent memory. April 5th to April 10th, 1815, we had an eruption of Mount Tambora. Now, Tambora is located on the southeastern end of Indonesia. So if we look at our little inset map of the world here, we have Indonesia, Java, and Sumatra. Sumatra down at the lower right end, we have what we call Mount Tambora. And if you look here, Mount Tambora, the height of the top of the volcano is 2,500 meters-ish, which is about 8,000 feet above sea level. This is the largest historical eruption. Now, what does that mean? Since we started keeping records, this is the largest eruption that has happened in world history. And what happened here? Well, we think there were several things. One, we have on this setup right here, we have a subduction zone. We have ocean floor diving under Indonesia and Sumatra. Plus, we probably also have some sort of mantle plume going on here. Watch the videos, giant bubbles of material that are coming up from below. And we had a volcano that was developed along this region. And as the volcano started to erupt, there is a possibility that water actually made its way in and interacted with the magma, and we got one terrifying explosion. It would be like the equivalent of like throwing water on a grease fire. Never do that. So a massive explosion. The explosion was enormous. It was so enormous that the volcano lost nearly a mile of its height. Right? So the edifice is the actual physical structure sticking out of the earth, right? Lost nearly a mile of its height. It generated humongous pyroclastic flows, which are clouds of rock and gas that can reach speeds of up to 100 miles an hour and have temperatures many times that of boiling. We had giant columns that shot up into the sky and shed pumice that were 20 centimeters in size, which is something like this. It generated a moderate tsunami. Why? Because if you're throwing a lot of material in, plus you have the force of an explosion, waves are going to travel outward from it. Killed approximately 70,000+ people, mainly from starvation. Some died from the tsunami, some died from the pyroclastic flows, but given the lower population in the region, most of them didn't die immediately from the volcano effects. They died, or the volcano effects, the pyroclastic flows, and the pumice stones. What did they die from? They died from starvation after because it affected their crops. Again, 120 million tons of sulfur ejected into the sky. Again, we had a red-colored sun. You could look at the sky. There were reports that you could look up and look at the sun unaided. And we know that even during a solar eclipse, we can't do that. Why? So much material in the sky. So what happened? That was 1815. A year later, May 1816, we had frost destroying crops in North America. We had a foot of snow in Quebec. Excuse me. In July to August, we had river ice in Pennsylvania. I grew up in Pennsylvania. Ice is not something that you'd expect that late in the year, especially not ice in the rivers. There were reports that on the scale of a few hours, that the temperature would go from, say, 95 degrees to freezing. Now, what causes that? Instability of the atmosphere. If you have, and we're going to see this coming back when we talk about the modern science and then some thoughts on it. If you have a fever, that occurs when your body goes up 1.5 degrees, right? So What are the manifestations of that? Sweats and chills, sweats and chills. Your body cannot maintain its normal homeostasis. In the same kind of thing, because we had so much variability of particulate matter aerosols in the atmosphere, their influence on all of the systems, a domino effect through all of the systems, caused massive changes in temperature, right? If you went outside and it was 95 during the day, when, for example, in Texas, 95 during the day, you expect at night that it's what? 70 degrees, 80 degrees. Sometimes when you walk outside, it might be 10, 11 at night, and you're still sweating when you're walking. For it to drop in several hours from 95 degrees to freezing, that is tremendous. Temperatures in New York City in 1817, even into 1817, reached a remarkably balmy minus 26 Fahrenheit. In the 19th century, this caused the worst famine in Europe, severe famine in China. So for the 19th century, 1800 to 1900, this was the worst famine seen in Europe and severe famine in China. We had famine here in America. We had crop loss. And so there were some lean times for people, not so much as in like widespread people are dropping dead from famine, but definitely lean times. So think about this. Largest historical eruption happened in 1815. The damage, so that happened in April, the damage persisted into 1816 and in some cases into 1817, the instability of the atmosphere. Largest historical eruption, 2 years. And what we call it is the year without a summer, because if we have a condition where we get ice into August, we effectively don't have a summer at that point, because when do we actually go from winter to spring to summer, right? We just bypass all that into fall or winter, and we're forced to eat robin's minstrels, right? So this is the idea that we have here. Still 2 years. It inspired Mary Shelley to write Frankenstein and Lord Byron to make more poems, because they were essentially stuck inside by the dreary, rainy conditions of the region. And Lord Byron said, hey, we've been reading ghost stories, sort of folk tales, etc. Why don't we all try and write some dark and gloomy story? Mary Shelley pens Frankenstein, Lord Byron writes some poems, right? It was sort of a writing competition between them. Think about that. The influence of that was so severe and so marked that people looked at it and said, why don't we write about this? So, an excerpt from Darkness by Lord Byron. I had a dream which was not all a dream. The bright sun was extinguished, and the stars did wander darkling in the eternal space, rayless and pathless, and the icy earth swung blind and blackening in the moonless air. Morn came and came and brought no day, and men forgot their passions in the dread of this their desolation, and all hearts were chilled into a selfish prayer for light. Now, was it that severe? It was severe enough that it sparked something in him to pen something like that. Morn came and brought no day. Of course, there was a day, but compared to what they were used to, now that they could look up and see the sun unaided, that was dramatic for them. That's amazing. But still, 2 years. Later in 1883, we had the eruption of Krakatau. Krakatau was also in between Java and Sumatra in Indonesia. It created a shockwave that was felt around the world. It actually propagated around the world and was recorded on pressure gauges 7 times, right? Each time decreasing. It blew out windows up to 3,000 miles away. It was impressive. But it also caused a reddish colored sky. Edvard Munch's The Scream, when he painted it, the idea of the sky in the background is something that when we look up, we don't want to see that. We don't want to go out and see a sky that is red. If you do, that usually is something like, I don't know what that is, but I'm not liking it. So in the idea of The Scream, that made sense for that sort of emotional attachment to it. Did Krakatau cause climate change? Well, it did cause a slight cooling of the atmosphere, but it didn't even really last a year. People marked the eruption itself, but not long-lasting effects from it. So think about this. Largest historical eruption, what did we get? We got at most 2 years. The Laki fissure eruptions, about a year. Krakatoa, which was a tremendous eruption, half a year to about a year. So if we say, well, what about something like Yellowstone? Well, it has been hypothesized that Yellowstone may actually influence global climate up to 8 years. And 8 years would be dramatic for one thing. Think about how interconnected the food network that we have. I can go to the store in America and buy apples that were grown in New Zealand, which means that we have a system that can get the apples from New Zealand to market for me to pick them up while they're still ripe. Sure, all the chemicals and stuff that are necessary to do that, all of the fast travel, but that can happen. If we have a system now which is interdependent so that people get food from all these different places, think about what that means if we start interfering with global harvests. Because now it's not just, well, there are no apples now, right? But think about all the other things that would be affected. And if we start affecting the basic things, corn, grains, now we run into some serious problems because those are staples of the American diet, staples of any diet, right? Rice, for example. So with Yellowstone, and watch the volcano video, with Yellowstone has never been associated with a major extinction event, right? Local, sure, there's local problems all the time, right? If we look back historically, we could look at damage that Yellowstone has done to the local region, ash that has been broadcast. So we know things have died because of Yellowstone, but no major worldwide extinction. We don't have that. We never have had a technologically advanced society living next to it that depends on global food, global communication, things that don't like ash. So we could have problems associated with that. And if it lasts 8 years, 8 years is a long time. We could see even with coronavirus, the interference with society right now on the order of now 6 months, 7 months. The world seems to be going crazy. The systems still work, but then we'd have the time to go, okay, let's try some new things. Because right now we're seeing the problems associated with it. Farmers can't get their milk to market. They can't make cheese because of all of the individual little domino systems that we have this remarkably efficient system. We have one hiccup and there are problems. Imagine if we stretch this out not 6 months, but 8 years. There would be problems that are more social, right? Wars that spark up because of resources, etc. But climate, if we're just talking climate, 8 years, right? The effect on us is much more severe, but still 8 years. So that means they're safe, right? Let's talk about those really big eruptions. If we do that, one of the best examples of this are what we call the Deccan Traps in India. If you look at this map here, we see this dark spot, what we call the Deccan Traps. These are lava flows that erupted in the past about 65 to 66 million years ago, originally covered an area of India about twice the size of Texas, 600,000 square miles, but had been reduced by erosion, and the lava flows would have been able to reach the Bay of Bengal. Some of the largest lava flows traveled over 1,500 kilometers, which is about 1,000 miles, to the Bay of Bengal. So why do we care? Well, think about this. If those Lackey fissure eruptions were able to affect global climate for a year, and that was 14 cubic kilometers, well, this is many times that. How many times that? The estimates are that this could be upwards of 500,000 cubic kilometers, right? And I'll show you a diagram here in a moment. Today, we can see the effects of here. Here's the Mahabaleshwar escarpment. Basalt flows over 1,200 meters thick, 1,200 meters, 3,600, about 4,500 feet, just shy of a mile, right? What you're seeing here are lava flows, and then the layers in between them are eroded old lava flows. So stacked like a series of pancakes, that you'd get a pulse of lava, and then it would erode some, and then a new pulse would come on top, and a new pulse, and a new pulse, like stacked pancakes. We have vast deposits that say, in the past, there were some crazy lava eruptions here. So how big is a cubic kilometer? I've been mentioning it the entire time. Well, it's still hard to wrap your head around. When we talk about something like a cubic kilometer, 3,280 feet on the side, who cares? If I hold up my fingers and I go, okay, this is a cubic inch, Most people can rationalize that. If I hold up my hands and I say, this is a cubic foot, most people can rationalize that. Even if we were smart in the metric system, a cubic kilometer is a strange thing. So here's the Eiffel Tower for scale. 3,280 feet on a side as a cube. And the Deccan traps in India 65 to 66 million years ago were about 500,000 of those. That is an insane amount of lava. It is so insane. The thing about this, 14 cubic kilometers was a football field 3,000 miles deep. So what would this be, right? 100 times that. If we do that, then we get 14. A lot. So let's try and put it into another perspective. Here's the Houston Astrodome. If we look at the circle of the Houston Astrodome, I recognize we're talking about a sphere, but if we look at the circular plan and then try and shrink that down, if we keep the same dimensions, at least two-dimensional dimensions, that circle has been exaggerated by 20,000 times. That circle represents the Houston Astrodome, and the big circle represents the flood basalts, something that is an unfathomable amount of lava. Even if the concentration of gas was remarkably low, that's still a lot of gas. So that circle has been exaggerated, but we get the idea of a vast amount of material. So surely this had to have had a tremendous effect on the planet. Maybe. So for a busy table here, let's break this down. At the end of the Cretaceous period, remember we have Jurassic Park. Well, actually most of the dinosaurs that are shown in Jurassic Park were actually from the Cretaceous period, which is more recent. The Cretaceous period ended 65 million years ago. And then we get into the age of mammals, which has been 65 million years to present, right? Where mammals dominated the planet. If we look at this, at the end of the Cretaceous period, what killed the dinosaurs? Open question. We're not sure. We know that an asteroid struck the planet, and that's what's labeled there at the bottom. It's 65.8 million years ago, we had the Chicxulub impact. If you know anything about the destruction of the dinosaurs, if you love dinosaurs and you've read them, right? If not, listen to kids. Kids will tell you everything that there is to know about dinosaurs. In the Yucatan Peninsula, if we look at Mexico and we have the Yucatan, which sits up there in the Gulf of Mexico, Florida's over here, and the Yucatan is right there. There is the evidence of an impact crater that is up to 200 kilometers in diameter. 200 kilometers is about 120 miles, 125 miles in diameter, buried by the jungle. We found out about its existence because oil drilling in the region was doing mapping of the subsurface, the stuff below the surface, and they ended up finding a very weird feature that sort of was roundish, but as they scanned in 3 dimensions, so roundish in cross-section, when they scanned it, it was a series of concentric rings that had a central peak. And they went, this just looks like craters on the moon. So the suggestion was some massive thing, about 6 to 10 miles wide, struck the surface of the Earth, potentially creating earthquakes of magnitude 9 or greater over a massive area of the Earth. And there is a lot of evidence that that was associated with the very end of the Cretaceous period. This slammed, and then shortly thereafter, and I use the term shortly loosely, shortly thereafter, dinosaurs died out. Shortly after the Chicxulub, we had another impact, the Voltage asteroid, right? And then potentially yet another asteroid just 0.3 million years later, right? So Chicxulub, 0.1 million years later, Voltage, 0.2 million years after that, right? Another asteroid. Chicxulub is the most important of those because it's certainly the biggest. But why do I put in those other two? Because if one managed to interfere with global climate, then if something is already interfering, it's like adding salt into a wound. Bang, bang, bang. At the same time, we have massive outpouring of lavas in the Deccan traps. So one could argue this: what killed the dinosaurs? Yes. Was it the asteroid? Was it, or the asteroids? Was it the lava? Both had to have some influence. And it has been an open question since we have discovered that asteroid impact crater as to which one is the most important. Is it that the asteroid killed him and the other stuff was just icing on the cake? Is it that they reinforced each other, that they hampered each other? What's going on? There are a large number of scientists that are proponents of asteroid only, as in the other stuff, while it was effective, it had no candle to the Chicxulub impact crater. There are others that suggest that because the timing of the extinctions wasn't just one extinction, that some of them were already dying, some of the dinosaurs and the sea creatures were already on their way out, that it couldn't just be one event. They're already dying over a period of time. So something had to already be affecting the climate. And if it affects the climate, like with famine, it affects the vegetation. If it affects the vegetation, herbivores die, carnivores start dying after them. So this would be like the 3 and 4 of the 1-2 punch. We have a whole bunch of stuff happening at once. Well, the interesting thing is, just last month or the month before, a new research paper came out and suggested this, that we had runaway global warming, we had runaway global cooling of the atmosphere as a result of the asteroid impacts. We had these temperature highs, but then over the course of 0.3 million years, the temperature started to plummet, and that caused a rapid extinction of the dinosaurs. But one of the new pieces of research suggests that the carbon dioxide produced by the Deccan lavas actually helped to warm the atmosphere up, so it sort of moderated each other. As in, it isn't just cooling, we had a nice little blanket on the bed that helped keep us a little bit warmer, so it stabilized the climate so we didn't get a precipitous dump off and even more stuff died. Why am I telling you any of this? Because it shows that the Deccan lavas could have a profound influence on the planet. And if that recent research is to believe, in that case, the warming was beneficial in the circumstance that it had to deal with. So depending on what's going on, aerosols, if we get a lot of aerosols that are produced, that can actually cause global cooling. Why? Sunlight comes in and is reflected off to space. If we get a large carbon dioxide output, that causes global warming. So a volcanic eruption, in this case, producing largely what they estimate to be carbon dioxide and other things, sulfur dioxides, actually helped to keep the planet warm to mitigate the precipitous drop-off in temperature caused by the asteroids. Why did the asteroids do that? Dust into the atmosphere, stuff reflects off it off to space, but the heat that we still had was being kept longer because of carbon dioxide from the lavas. This is what makes science so cool and the discussion so sometimes infuriating. Because we can't just look at one thing and cherry pick that information out and then say, well, there's the answer. No, because in this case, they actually were working against each other. In the case of a volcanic eruption, if it produces a large amount of aerosols, that can actually cool the planet down. That could be a good thing, unless it's too extreme. So when we actually talk about eruptions like this, when we talk about eruptions, period, we need to be able to understand which has more magnitude, right? What is the trend of the environment? If we're getting a warming and then we suddenly get more aerosols, then we get a cooling, that interferes. So what scientists usually have to do in order to try and tease out what's going on here is they have to apply computer modeling. And computer modeling tries to take the wide disparity in information that I just discussed and try to work through reasonable permutations of the data to try and see what best fits historical developments. For example, if we look at anything that we have not seen, any big ticket item that we have not seen, for example, how did we get our moon? Was it something that just swung by and we captured? Well, no, it doesn't look like that. Why? Because it's too big for us to capture. Well, then how did we get it? Something hit the earth and it ejected material. Did it? Let's run computer models. We have the earth, we have various different possible impacting things. We see debris that goes out, put in the gravity parameters, see if it captures the information, captures the material, builds a moon. We can run it so fast that it can give us a whole bunch of different answers. And then we go, do these answers seem to jive? And if they're like, no, that's impossible, because it would have had to hit the earth and then the earth would have blown. So we can then go, okay, we can throw those out because those don't make any sense. But these seem reasonable. And from those, then we can devise tests. Actual go, grab a sample, bring it back, study it in the lab. This is no different. If we have so many competing data streams, then what we have to do is we have to run a whole bunch of permutations. And that study that I mentioned to you about just recently, they did that. They ran a series of chemical studies, atmospheric studies, looking at past history, and then trying to tease out what the influence of the Deccan lavas would be versus the asteroids. Does that mean that that paper that came out recently is the definitive answer? No, because the debate has been going for about 50 years. So it's one of those things, as we get more information, we get more refined, and then instead of going, is it this or is it this, how much of it is this versus how much of it is this? Because we know they both have to have an influence. Have I confused you yet? The other thing is, though, when we talk about those, we always have to be careful with models, because we have to remember at the end of the day that it is a model. We always have to take our model and then we have to test it against real stuff, because a computer model can spit out an answer, but that doesn't mean that it's a useful answer. That doesn't mean that it's a valid answer. We've all done this as kids or as adults. We take the calculator, we punch in some numbers, and it gives us an answer, and that answer is wrong. Why is the answer wrong? Because it gave us the correct answer based on what we typed in, but what we typed in might not have been what we should have typed in, right? We wanted to go 2 + 2 = 4, and we look and we go, why is it 5? Because we hit a wrong number. It gave us the answer based on what we put in, but maybe we put in the information wrong. So we always have to be careful with models, because they require us to put in the information. If that information is wrong, we get an answer. That answer might not be useful or valid. So we always have to be careful. One of my favorite examples of that thing came out recently, because we have been modeling climate change for a while. And the models have, by and large, followed along with the actual increase in temperature of the planet. So we go, the models are accurate, right? Temperature did this, the models say that the temperature should do this, they line up, awesome. Well, about 15, 18 years ago, the models predicted that we should get a lot more warming than what we actually got. Well, we're going to talk about this with the politics. Immediately people went, see, the models lie. You can't trust the models. You must throw them out because they said it should be warmer. Obviously it's not. Global warming's a hoax. Wait a minute. We have to look at what went into the models, right? And then maybe some new thing has come along, or maybe the models only worked, but as we started going through more and more permutations, more and more years of the data, there became an error in the data, or something that, when building up over time, caused it to diverge from reality. I saw a study that came out of MIT that said this. It said, we know what the problem is. We haven't been taking into account small volume volcanic eruptions, which produce aerosols, which can actually cause cooling. So we predicted this, and what actually happened was less than that. If we take them into account, then our model fits. And I thought about that in my office, and I started to laugh. And had anybody walked by at that time, they'd have been like, okay, it's the crazy guy in his office laughing about geology. And I went, wait a minute. But if you only take into account the small volume eruptions in the last 15 or 20 years, then sure, the end of this comes down and does this, and it lines up. But you'd have to take into account all of the small volume eruptions for the rest of the model, and the rest of the model without them jived. If you now take them into account, it won't jive anymore. So we can't just do cherry pick. And I'm not saying, do scientists cherry pick? Sometimes they shouldn't, but it happens. Why? Because we're all human. And this is one of the things that then drives into eventually what we're going to talk about with politics. Because if we as scientists are trying to make statements that can then be used for policy, if we ever make an errant statement, it's like the sum total of your life is gone, right? You're a liar and you will always be a liar. I'm like, wait a minute. If we make a mistake, what they're saying is you must always be perfect, because the moment you're not perfect, you're done. And we have to be very careful as scientists. Unfortunately, there is the eye of scrutiny, like the eye of Sauron on us, right? If we move in a strange way with the ring, then we get into trouble, right? Then come the Urukai, right? So I hope that you understood or I hope that you got got some useful information from this. Volcanic eruptions can cause changes to the climate. The changes are usually small, on the order of 1 to maybe 10 years. Even our largest historical eruption lasted 2 years. The effects of it lasted 2 years. But if we look at our prehistoric eruptions, like the Deccan lavas, they may have actually had a countering influence and a mitigating influence on the damage done from an asteroid impact. So when people cite volcanoes as, well, volcanoes do more than people. Yes, sometimes good, sometimes bad, depending on perspective, depending on what's happening. And we always have to keep that in perspective. So what's the verdict? Think about it. It cannot just be one-sided. We cannot cherry pick data. We must consider the entire argument, and we must consider it long-term. So what we're going to do next time, my next video is going to be on modern climate change, and it is going to be on all of our modern data over the last 140 years, and then putting that into perspective, what that means, what we can use it for, how we can compare it to the past, talking about models, the limitations of the models. It sounds more daunting than it is, and it will be more stimulating than it sounds. So thank you. If you like this, we're going to get a better setup in the future. This is our early YouTube stuff, so it won't just be PowerPoint. There'll be more bells and whistles, but the science is what's important. Who cares about all of that? As long as you can hear me and as long as it's useful, that's what we care about.